Hey, welcome to Clients Calculus. Today we're going to look at Lesson 2.1, Rates of Change and Limits. Lots of good information in this lesson. What we're going to do is I'm going to give you an overview, look at a few instances, and then you can refer back to the Moodle for some more specific examples to help you through some of the algebra involved. So we're going to look at rates of change, think slope, and we're going to kind of look at how we can find a limiting value for some of these things. So let's look at it in general case. Suppose we're driving 200 miles, it's going to take 4 hours. We can find our average speed. We just take 200 miles divided by 4 hours, and we know on average we traveled 50 miles an hour. Our average speed is the distance traveled divided by the time it takes. We can call that our change in distance divided by our change in time. And if we looked at our speedometer at any point during the trip, remember, it would not always read 50 miles per hour. Sometimes it'll read more, sometimes it'll read less. And whatever the speedometer reads, well, that's our instantaneous speed. Okay? So in calculus, we're going to be looking at instantaneous speeds. What is our change at that moment? So we looked at the Tetons when we started this video, so let's think about a rock falling from one of those high cliffs. Okay, and it's starting, its speed at the top of the cliff is 0, but then it's going to fall off the cliff and it's going to increase its speed as it goes down. So think the position of the rock would be y equals 16t squared. That 16, recall from algebra, is just our coefficient due to gravity when we're measuring in feet. So after 2 seconds, if it's falling at those speeds, we'll put in a 2 for t, and we know after 2 seconds it's gone 64 feet. Okay, that's how far it's fallen. And the change in the speed then is going to be the change in position over the change in time, our average speed. And that's going to be 64 feet divided by 2 seconds. And the units are important, folks. We're going to need units this entire course. Think 64 divided by 2 is 32, and we've got feet per second. And that's our average velocity, or average speed, okay? And there is a slight difference between speed and velocity. Speed is always positive. Velocity, if it's positive, you know it's going forward. If it's negative, you're going backwards. So what is our instantaneous speed now? At 2 seconds, we know it's 64 feet down the cliff. We know it averaged 32 feet per second. But what is that speed at exactly 2 seconds? Because as I said to you, it's going to start at a speed of 0, and it's picking up speed as it falls down the mountain. So our instantaneous speed, we're still looking at a change in the position over the change in time. But think about this change in time. If we want to look right at 2 seconds, we're going to look at 2 seconds plus some very, very small bit of time beyond 2 seconds. Because you know when we're looking for that slope or that velocity, that change, we need to have two numbers to subtract. So we'll look at a very small change, which is going to give us 16t squared. Here's our time, 2 plus just a little bit more, minus 16t squared. Here's our time at 2 seconds exactly. And it would be over 2 plus h minus 2. So think of that as this 2 plus h minus 2. So that's why we only see the h when we look at this equation, okay? So now how can we calculate that? And we're just thinking of h as a very small number. So if you want to think concretely, we can use a calculator to evaluate this. That's the quickest way to do it. And what you'll see is, let's let h equal 1, 0.1, 0.01, smaller and smaller values of h. And we're just going to do it with your table function. Okay, you can put 16t squared into your calculator, and then you can, you can put this whole function into your calculator. And just consider this x, and then just put in these numbers for x and generate a table. And what we can see happening is as we're getting smaller and smaller, closer and closer to 0, we're getting to it, we're settling in on a number. You can see that we're settling in, we're getting closer and closer to 64 feet per second. So we say that velocity has a limiting value of 64 feet per second as h approaches 0. Now h can never equal 0 because we can't have h in the denominator of a function, but it can get very close. So this is one way to find these velocities. So, and we call that the limit, finding the limit as h approaches 0. So that's where that, and we call this the limit as h approaches 0. We read this of 16 times 2 plus h squared minus 16 times 2 squared all over h. And if I was going to simplify this, the first thing I'd do is I'd take out the 16s. I'd factor them right out. It's not going to make a difference. You can just put it in front. And as we go through this course, it's always easier if you see a common factor, get it out in front. Smaller numbers, just easier to work with. 2 plus h squared is going to give you 4 plus 4h plus h squared. And then as you simplify this, you can see that you can take out 4 minus 4 is 0. Oh, I need to stop writing on my board. It's already there. And the h's are going to factor out, and we're going to be left with 16 times the limit as h approaches 0 of 4 plus h. Now this is beautiful because we couldn't substitute 0 in for h here. Because if we did, we've got 0 in the denominator. Can't be done. But if we factor h out of this, notice now we can substitute 0 in. And we'll just get 16 times 4, which is 64, which is what we saw in the table. Now, we can look at those things a lot of different ways. Now let's look at y equals the sine of x over x. This one we aren't going to do analytically quite as well, but we always want to be asking ourselves the same thing with these limits. What happens as x approaches 0? Because the limits are just what the function intends to do. It may not be defined at that point, but what does it intend to do? So looking at that, graphically, we're going to put y equals the sine of x divided by x into our calculator. And we're going to, for our window standard, I would like to recommend to you folks that you just go negative 2 pi to 2 pi for your x's, pi over 2. Anytime you're doing a trig function, just kind of see what's going on. The y's kind of depends on the function, but you know sine of x goes from negative 1 to 1. So if we go negative 1 to 2, we know we're going to get it. Scale of just 1. So we're going to look at this in our calculator, and when we do, it will graph this function. Now if you look at that, you think, well, it's what the function intends to do. The limit as it approaches 0, well, shoot, it's 1. Not a problem. But now, if you look at it numerically, look in the table, you will see that when x equals 0, the function is actually undefined. If you plugged in, calculate a value in your graph, you would see that it's 0. But if you look to either side of this, look at it, negative 0.1, close to 0, it's 0.99. At positive 0.1, again close to 0, it's 0.99. So it intends to be 1 there. Just happens to be that it's undefined because you can't have 0 in the denominator. So this is going to be, so tables are a great way to look and see what limits are. Graphs, or the limit notation is a good way. So it's going to appear that the limit of sine of x over x as x approaches 0 is 1. That's going to be a fun fact for you guys to memorize. We will see after we study derivatives, we'll look at Hopital's rule, and we will see that we'll find an analytical way to prove that. But right now, we're just going to look at this table and say, okay, function intends to be 1 there, so anytime we see sine of x over x, we're going to call it 1. That's our limit. So limit notation. How do we write down? We want to know what a function intends to be. Well, the limit as x approaches any number c, this is how you read it, of the function f of x equals a big L, and that basically stands for the y value of the function at c, if it's defined, or what the y value intended to be if it's not. So we read that as the limit of f of x as x approaches c is L. And from what our last example, the limit as x approaches 0 of sine of x over x, that's our f of x, equals 1. That's our L, or our limit. So things to remember, and we're going to watch we watched the calculus phobe in class already. If you weren't here, pick it up on limits. That's on the Moodle. Limit of a function refers to the value that the function approaches. That's what the function intends to do, not the actual value. We're going to see some graphs of that in a few minutes. Right now. Okay, take a look at this graph right here. And we're going to go by ones here. So we think of this as 1, 2, 3, 1, 2. Now, the limit as x approaches 2 is not this x value. It's not what the function is. It's what the function intended to do. The function clearly intended, if you look from the left, it's approaching 2. If you look coming from the right, it's approaching 2. The function intends to have a value of 2 at this point, at x equals 2. So the limit as x approaches 2 of f of x equals 2. It does not equal 1. Oops. Okay, so now let's look at how to calculate some limits. We talked about just plug in the value that you're interested in. If you've got the limit as x approaches a number, well, to find out what the limit is of a function, you can plug in the number. A lot of times that'll get you there. So I can see the limit as x approaches c. It's a variable. So this is what's going to get plugged in to for all my x terms. And the limit is just going to be c cubed plus 4 times c squared minus 3. We don't know what c is. That's as good as it gets. So that's how you would evaluate the limit if all you're given is x is approaching c. Once again, x is approaching c here. So again, it's not an actual value, so I'm just going to put it in for x, and I'm going to get c to the 4th plus c squared minus 1 all over c squared plus 5. Well, that's not going to factor and give me anything to cancel, so I'll just leave that alone. And that's my final answer. Now down here for c, we want the limit as x approaches 3. Well, that's an actual value. So I'm going to put that in here for x, and I'll get 3 squared plus 5 times 3 plus 6 all over 3 plus 2. Work it out, and you've got 9 plus 15 is 24 plus 6 is 30. Over 3 plus 2 is 5. And the limit as x approaches 3 of all of this is 6. That's the fun. And if you graphed it, you looked at 3, that's what you'd see. It's defined at that point, and the y value is 6. Once again, limit as x approaches 3, I'm going to put in 3 squared plus 2 times 3 minus 15 all over 3 minus 3. Now we see a problem. What do we have? 3 minus 3 is 0. Can't do that. Do we have another strategy? We think about factoring here. If we could because the thing is we can't have 0 in the denominator. We know the function's undefined here, but what does it intend to do? I'm going to factor this, and we're going to call it the limit as x approaches 3 of x plus 5 times x minus 3. Because 3 times 5 is 5 times negative 3 is negative 15, negative 5x, negative 3x is positive 2x, all over x minus 3. Now these will cancel out, and I have the limit as x approaches 3 of x plus 5. Now I can substitute. So I'm going to put in my 3, and I know the function intends to be 8. It didn't get there. There's a hole in this function at that point, and I would recommend you graph it. Make sure when you're graphing it and your y equals, you put the parentheses around it. But graph it, take a look at it. You'll see that if you try to evaluate 3, it's undefined. But it's just a hole there. You can see from the left and the right, it intends to be 8. So it does have a limit. It might not have a value there, but it's got a limit. So, using substitution, that's what we just did. Plug in some numbers. You can see that's defined. You've got 9 times negative 1. Hope you got negative 9. Here, this is 2 plus 2, so you're okay. You can substitute. 2, 2, 2. 4 plus 4 plus 4, 12 over 4, 3. Easy to get limits when all you have to do is substitute. If you have to factor, you do that. There's also a conjugate method. There's a little video on that. I want you to check that out. Example 6. Does a limit always exist? Does the function always know what it's going to do? Heavens no. I don't always know what I'm going to do. I don't think you do either. I've seen you guys in the halls. So, exploring a non-existent limit. What happens when the function doesn't know? We look at this function. We want to find the limit as x approaches 2. Well, if you put 2 in the denominator for x, you get 0. It's undefined. It's not going to work. Can't substitute. If I factored, I'd have x plus 2 times x minus, or x plus 1 times x minus 1 over x plus 2. Nothing that can be canceled. That's not going to work. The conjugate method, there's no point. If I multiply numerator and denominator by x plus 2, I'm still going to get 0 down here. It's not going to work out. So none of these methods will work. They aren't going to find us a limit. So let's look at this graphically. Honey, this is what you need to wake up. Okay, if I look at this graphically, is this on here?
Yeah, let's see, it is, but I can't pick it up though.
Why not?
Well, I can see the calculator, but it's not backlit, so you can't see any of the calculations on it. It's too dark. There, finally.
Okay, you put your function in the y equals menu. I'm just going to look at negative 10 to 10. And when I graph it, you can see that coming from the left, it's going down to negative infinity. Coming from the right, it's going up to positive infinity. Well, if the function doesn't have any intentions of settling down to a number, then we have to say that no limit exists. So, and just a little more notation for you, the limit as x approaches 2 from the right, as we saw, it was going down like this and up like this. Well, as it approached 2 here from the right of f of x, that's going to positive infinity. But the limit as x approaches 2 from the left of f of x, that's over here, it's going down, that's going to negative infinity. Well, if they don't agree on where they're going, you say it does not exist. Okay, the limits from the left, the limits from the right have to match in order for a limit to exist. So if the limit does exist, the nice thing about it is it's just a number. We can add, subtract, multiply, divide, multiply by a constant, raised to a power. Anything you can do to a number, you can do with a limit. There's a big book of theorem, or a big page of theorems in your book about that. But keep in mind, these are numbers when you've got a limit. So that's why you can do all of these things. But you can only get that number if it's the same going from the left and the right. Okay? And we can say the one-sided, remember, if it's going, if you think about a function, here's the point we're interested in. If you look at it coming from the right, that's the limit as x approaches, we'll call this c, from the right. So we make a plus sign there to find that value. And if we were looking at it coming from this side, we say it's the limit as x approaches c, and we put a little minus sign because these are all the negative numbers as you go left. So, of f of x. So, going from the right, we do have one-sided limits. You can say the one-sided limit exists. It's whatever this value is. Going from the left, it's the same value. If it's the same from the right and the left, then you say it exists, and that's what it is. Let's look at this one. Look at some examples of this. At x equals 1, well, the function wants to be 0 coming from the left, and it wants to be 1 coming from the right. So we're going to say we got a little problem here. It wants to be 0 from the left. It wants to be 1 from the right. So an f of 1 is 1 because that is where it's defined. But if these two don't match, then we say the limit doesn't exist. The value of the function exists. We know what it wants to be from the left and the right. But if these don't match, we say it does not exist. Let's look at another one. Let's look at x equals 2. Take just a minute, tell me from the right, the left, and what the values are, what you think they are. Okay. X equals 2. The limit from the left is 1, because you can see it coming over. The limit from the right is 1. The actual value of the function is 2. But notice these limits match. So the limit as x approaches 2 of f of x is 1. That's what it intended to do. Just got a little jumpy right there. Now let's look at 3. So now we're looking at this point right here. Well, from the left, it approaches 2. From the right, it approaches 2. The actual value of the function is 2. So in this case, the limit is the same as the value of the function. The limit as x approaches 3 of f of x is 2. Because the left and the right match, it has nothing to do with the value of the function. Sandwich theorem. Sometimes the algebra gets a little ugly. Sometimes, like the sine of x over x, they're hard to evaluate. All the sandwich theorem says is if you've got a function that's hard to kind of get a hold of, like f of x, like sine of x over x, but you know what it's between, that it's between two things that you can nail down, then you know, if you know these two limits, the limit of this has to be between them. That's basically what it means. If you read it in notation, if g of x is less than or equal to f of x, which is less than or equal to h of x, for all the x's not equal to c in some interval about c, and the limit as x approaches c of g of x equals the limit of x approaches c of h of x equals L. So these two are the same. If these two limits are the same, then this limit has to be the same also. The limit as x approaches c of f of x also equals the limit. Okay? So let's look at this nice messy function. We want to show that the limit as x approaches 0 of x squared times the sine of 1 over x equals 0. We can't just directly substitute. We can't have 0 in the denominator. So we know, though, that the maximum value of the sine is 1. The sine function goes between negative 1 and 1. So x squared times the sine of 1 over x has to be less than or equal to the x squared, because 1 and 1 squared is the same. The minimum value of the sine of sine is negative 1. So we also know that x squared times the sine of 1 over x, this whole thing, is greater than or equal to negative x squared. Because if you have negative 1 and you square it, there you go. So what we can do here is we've got a function, then we can say that negative x squared is less than or equal to this function, which is less than or equal to this function. And once we've done that, we can take the limit of each of them. there's nothing says I can't just substitute 0 in here and here. And if I do, I get 0 for these functions. Since this is between them, the limit of this function is also equal to 0. Sandwiches, what's in between? So, and if you look at it in your table, first let's put it on the graph. I want to take a peek at it. And we're just looking at very little value. We're looking between negative 2/10 and 2/10 by 1. And our y, we're going from negative 0.02 to 0.02 by 0.01. And so looking at it very small, you can see here's your x squared, here's your negative x squared, and here's this x squared times the sine of 1 over x. You can see it oscillating in between them. And you don't get a good idea of what that intends to do, but right here, since this is 0 and this is 0, at this particular point at x equals 0, we can say that the limit is 0 by the sandwich there. Okay? Now, that was a big look at all of that, or a quick look at all of that. What we're going to do is we'll spend, you can see, 4 days doing all of this. You'll see it, it's on the website, and it's also, you'll see it in class, and it's posted up on the board. So we're going to work working on these when you get to class, and then the next day we've got some more. The next day we've got some more. We're going to do some partner work and some turn-in stuff here. And this graphical approach, this worksheet, is a wonderful thing. So hope you enjoyed your first look at limits.